Smooth surfaces, maximally many lines. So.
First of all, I want to thank the organizers for inviting me to speak. It's great to be here. Karen's birthday. Oh yeah, maybe I should stand closer to that. So I wanted to say maybe a few words about how I know Karen. So I'm actually her grand student, so my advisor is Kevin. But I really got to know Karen when I was a postdoc at Michigan. And I came to start to be a postdoc at Michigan in fall 2019. We went to this wonderful conference that Karen helped organize. We ran a project in called Women in Putative Algebra, and I'll talk a little bit about work that came out of that conference as well. And then as everyone knows, we were meeting in person for a while, and the world completely shut down that spring. So things had to look a little bit different when we started to do more research back when everything was shut down. So I introduced Karen to Slack, which at the time was free and had unlimited use. And I think she was a little hesitant.
And I love it, except then they changed it again. So.
Yeah, now it's not free anymore. But she was a little bit hesitant for the technology at first, and then she realized that she had access to all of us, like 24 hours a day. And so I think we had a really productive time. We got a little bit carried away sometimes. I have a distinct memory. We used to, when sort of projects were wrapping up, and we were really excited about something, we would be messaging, and one of us would see the other was online, and we'd just say, you want to Zoom right now? And we would just Zoom right then, because we had nothing but better to do during the pandemic. I have a distinct memory. At one point, I got a text message and realized I'm on a Zoom with Karen, and I was supposed to be at a friend's house for a New Year's Eve party because it was 9 p.m. on New Year's Eve. So anyway, that gives you a taste of sort of like what working with Karen was like, but I really enjoyed it. So happy birthday, Karen. All right, so I'm going to talk about, the main paper I'll talk about is joint work with Tim Ryan, who's also here, and Karen, called something like Smooth Surfaces with Maximally Many Lines, and it's on the archive currently. But I'm going to mention related work also with Anna Brosowsky, who's also here. And then other related work, this came out of the Women in Putative Algebra conference with Zhibek Kadyrsizova, Kenkel, Jyoti Singh, Karen, Adela Vraciu, and Emily Witt. All right, so maybe I want to start setting some notation. So throughout, X, I'm going to write it as, yeah, that is going to be a reduced homogeneous polynomial. Is going to be a smooth surface of degree D. And maybe because I'm going to forget, so I won't always need algebraically closed. I will try to mention when I need algebraically closed, but in case I forget it, you can just assume I'm always talking about an algebraically closed field. And I want to start with the following motivating question. How many lines can such an X contain? Is this big enough, by the way, for people in the back? Great. So maybe as a warm-up, if D is 1 or 2, right, it's not that interesting. For D is 1, we just have a plane. For D equals 2, we have a smooth quadratic surface. That's something like this. It's got lines in 2 different rulings. And quadratic surfaces will show up later in this talk. But we always have infinitely many lines in both of these cases. Right? And then when D equals 3, maybe Kevin will be surprised to learn what he taught me back in grad school, that we always have 27 lines. Said there are many lines.
Oh, I've been told, I know.
Nothing over an algebraically closed field, otherwise you can have less. So 27 is a lot of lines. It's the most lines you can contain on the cubic surface. It's also the least lines you can contain on the cubic surface. But it gets more interesting when D is bigger than or equal to 4. Generally, we have no lines. But we can come up with bounds for the number of lines a surface of degree D can contain in terms of degree. All right, so maybe the very first bound is really classical, so it's the Clebsch back in 1861, and this is over the complex number, and it says x has less than or equal to 11 d squared, and it's 24 d lines. Smooth surface of degree d. Oh, and maybe from now on, I want d to be bigger than or equal to 3 just to avoid these cases of infinite lines. So I probably work it to the right end. Great. And actually, if I plug in d equals 3 there, I do get my 27.
Janet, it's 24D.
Oh, yeah, sorry, 140. Great, thanks. That's even in my notes. The next result was due to Segre. So like 80 years later, 1943, also over C. And he says less than or equal to, same leading term, 11d squared minus 28d plus 12. So he just strictly improves this bound. And then the newest result is actually very recent. It's Bauer and Rams. And this is 2023. No, yes, 2023. And they show, so not just over C, so now K is characteristic 0, or characteristic P strictly bigger than the degree. So for a large P, which kind of behaves like characteristic 0 in this case, I get 11d squared minus 30d plus 18 lines at most. All right, so we've got sort of our best bound. These are just all strict improvements, right? This is our best bound. And so the first thing you might ask is, are these bounds sharp at all? And the answer is no, except when d is 3. So when I plug in d equals 3 to all of these, I should get 27 if I've written the numbers right. If you don't get 27, then I've written one of these bounds wrong. But as an example, even when d equals 4, and let's do this case where the Bauer and Rams bound holds. So this is characteristic k is 0, or p bigger than d, then there's an example. So what's called Schur's quartic. Q plus CW. This guy has 64 lines. And actually, Rams and Chu show that this is the most you can have in these cases. This is 2015. But so the most number of lines you can have is 64, and we actually can attain it in this case. But if you plug in d equals 4 into this thing, if I've written it correctly, you should get 74. So this bound is not sharp when d is 4. And maybe I'll mention a little aside. There is some work into trying to figure out what a sharp bound is in characteristic 0. So maybe I'll just briefly talk about it. Question?
Janet, what do you mean by that they showed this was the most you can have?
For d equals 4, I think that's maximum for lines.
Yeah, so in the case that we're over a field of characteristic 0 or characteristic p bigger than d, there are no surfaces of degree 4 that have more than 64 lines.
I see. Okay.
So they exhibit one with 64 lines, but there are no surfaces with more than 64 lines. However, this bound would just say that you always have less than or equal to 74. Okay. Yeah, other questions?
Is there any, all of these bounds are quadratic formulas?
Yes.
Yeah, I'm confused. Like, why, is there any reason why that should be obvious at first, or?
is there reasons why this is obvious? I don't know that, well,
It won't be quadratic.
it won't be quadratic in characteristic P. There's a very naive bound in characteristic P that I can explain that's not quadratic. But yeah, so this will only hold in these cases. That's the next thing I'll do. Where the quadratic one is coming from, I guess this Pagoda locus maybe is Tim, yeah.
Yeah, it's
So
like-
there's something you can compute. This bound comes from computing a set of points where there exists a line through a point with intersection multiplicity with my surface at least 4. And that you can like actually compute that thing, and that will contain all the lines on your surface, and it's something of like you basically the quadratic thing comes out of that, the degree of that thing. So yeah, I guess that's kind of where this bound is coming from, section theory. Yeah.
In this case, you don't have to head how many lines are on the Fermat coordinate?
40.
40.
In which
It's
characteristic?
like a good characteristic. 0 or like.
Isn't it 3D squared?
Oh, I just meant p equals 4.
Oh,
Yes,
whatever
40,
3
whatever.
times 4 squared is.
Okay, thank you.
That one is quadratic too, no? So your bound has to be at least quadratic. In characteristic 0.
And characteristic 0, yes. Yeah, so I'm not going to give a sharper bound in characteristic 0, but I'll tell you about a little bit of work that's been done in characteristic 0. So maybe aside. Okay, so Postieri and Sarti have a paper in 2007 that constructs a lot of, or some surfaces with a lot of lines in characteristic 0. So maybe I want to say surfaces with, and what they construct is with 7d squared minus 12d in characteristic 0. And there's 3 kind of ways they do this. Maybe I'll just talk about one of them, but one way is surfaces of the form QXY plus QW. So sort of being able to split it into pieces with just 2 variables and just 2 variables, and actually if this function is the same, then you kind of get more lines. And maybe they do this not for very many degrees, but for d equals 6, 8, and 12. And maybe there's a conjecture that this is actually a sharp upper bound. This is the one you get, this should give 64 when d is 4. So yeah, one way they do it is constructing surfaces like this. I guess another way they do it is they construct surfaces with like automorphism groups. And another way they do it is they construct a surface which is branched over a curve in P2 that has many total inflection points. So there's sort of 3 ways they construct these surfaces. Okay, the next natural question you can ask, so this bound is not sharp, but also you could ask if it holds outside of these assumptions, right? You could ask if it holds in characteristic P less than D. And the answer is no. So for example, then let's do the d equals 4 example. And let's pick a characteristic less than 4, so that p equals 3. Then this guy, our Fermat in degree 4, has 112 lines. So our bound should have said 74, but we have 112 lines. And actually, Rams and Chu, in a separate paper in 2015, showed that this is the most lines you can contain.
In any characteristic.
No, what in characteristic 3?
Oh, characteristic 3.
Yeah, characteristic 3 d equals 4. I need degree 4 surface in characteristic 3. Although I guess, so I think actually they do show, okay, so I think actually in their paper, the only remaining steps, so they've already kind of said that in these cases, you're less than 74. Or sorry, that was Bauer and Rams, but there was already a bound, or there is a bound that says less than 74. And the p equals 2 case is due to Degtyarev in characteristic 2. So there's 60 lines there at most. Yeah.
Can I ask a dumb question? So they checked only for the equals those 3 numbers, then the upper bounds, like you have basically 3 numbers and you could have predicted any formula. Why 7d square minus 12d, given that d is only for like 4, 8, 12 or 6?
Is there one other d they do?
Or
I mean, it
still
works
it
for
is
3
just
and 4 as
finitely
well.
many, so.
Oh yeah, so it also works for 3 and 4.
It's just that those are sort of,
So I think maybe that's how they come up with this, is they just interpolate and they find something that fits. I don't know. But yeah, this bound works for 3 and 4, and then those degrees. I don't know. This is not really. I don't know that they strongly conjecture that this is the maximum number, but it's possible. So I don't know. It could be, but it's kind of interesting that I think there's not examples with leading term 11d squared that people know. People have not constructed examples in characteristic 0, at least as far as I know. With 11d squared lines, they're like, of course, for small d though, you can't really tell what the polynomial is. Other questions? Okay. All right. So is there a bound that works for p less than our degree? And the first answer I know is actually due to, it's in a paper of Kollar's, and it's kind of it's a quick proof, it's a short remark, so I think he calls it a proposition. So the number of lines on X, and this is characteristic 3, is less than or equal to d to the 4th. And this just comes from plugging in what it, like taking an equation of degree d, understanding what it would mean to have a line on X, and then sort of plugging in my possible lines, and then using Béziers theorem to say how many solutions I have. I get polynomials on the coefficients, and this is what happens, but this is what pops out, because I have at most 3 to the 4 lines. All right, but this bound is not sharp. So we can do better. So presumably come out at some point. So again, so X is smooth. Degree t. A surface. In any characteristic. I should say here, okay, I'll tell you why I need k equals k bar. Then the number of lines on X is less than or equal to, therefore, 3d cubed plus 3d squared. So we give an upper bound, and we also prove it's sharp, and we're going to classify exactly when it's sharp. So with equality, it can only yes. Maybe let's write this again and do it up. After some change of variables. That is the Fermat. Degree q to b plus 1. Where our our field now is going to have characteristic P. I guess E is just some number bigger than 0, a natural number, and a characteristic of K. All right, and maybe I'm going to call this, I'll verbally probably call this the Fermat of degree. Great. Questions on the statement of the theorem or anything so far?
This does not contradict the previous bounds.
This does not contradict the previous bounds. So in particular, this is a lot bigger. So the previous bounds had 11b squared as their leading terms. And so this bound is a lot bigger anytime b is bigger than 4, bigger than or equal to 4. So at d equals 3, if I've written this right, I'm pretty sure I've written this one right, but you should get 27. And all the other bounds also get 27 when d is 3. And when d is 4, this is going to be much bigger than all the other bounds. So we're saying the number of, so yeah, so we can still, this still holds in characteristic 0. Of course, it's not as interesting there because there are better bounds known in characteristic 0.
But you said they are achieved. Right?
Yeah, so it works if and only if
Characteristic P.
we have
With
characteristic
less
P.
than
That's the other one.
Yeah, so we get equality only when the characteristic of our field is P. Yeah, great question. Other questions? Okay. So maybe I want to talk just a little bit about some of the ideas that go into this proof. And then towards the end of the talk, I'm going to relate this to other work we've done and relate this to F-singularities, which should be more familiar to people in this conference. So okay, so our rough sketch. All right, so for the upper bound, so it's kind of a neat proof because first we bound the number of lines intersecting a fixed line L. Geometrically. And I'm not going to write out sort of our whole argument, but the idea of this is we use the Euler characteristic to bound the Picard number, so the rank of the Nernst-Severi group, which is our divisors modded out by, actually you can do any equivalence you want on the case of smooth surfaces, but you can think about plotting out by numeric or algebraic equivalence. And then we find a set of lines intersecting a fixed line L that would be numerically independent. And so we can't have sort of more than the Picard number of those lines, and then we're able to count all the lines intersecting a fixed line L. And I'll talk more about this later, but a lot of geometry of our surface pops out when we achieve our upper bound from this argument. And then 2, we bound the number of lines skewed to a fixed line L. Algebraically. And by algebraically here, I mean this is very similar to Kolar's proof. We're sort of writing out, we decide that our fixed line L is the vanishing set of xy. We write out what it would mean for our surface to contain that line. We write out what it would mean for lines to be skewed to it. And we just use Bayesian's theorem on the coefficients we get on our lines. And we get a bound for the number of lines skewed to a fixed line L. So this conference is called Singularities in Algebra and Geometry. You can see we have sort of both things coming in to our theorem. And then our classification, this equality part, a little more involved. Sort of uniqueness. All right, so maybe I'll make a note first. So we studied lines on the Fermat of degree u to the e plus 1 in characteristic P with Anna Brosowsky. Somebody else say. Oh, E comes first. So we know a lot about the configuration of lines on this Fermat. This configuration of lines forms a special configuration that has been studied before, called a Hermitian generalized quadrangle. And what we do in this case is we show, so we use our geometry from 1 to find or to show that our lines form a special incidence structure. Actually, our lines are the planes containing them. So one of the things that pops out of this upper bound is that if we had as many lines as possible, meaning if we hit our Picard number with just lines, actually then our Narron's Gray group is generated by lines, then every single line, when it intersects another line on our surface, there's actually going to be D lines in that plane, spanned by those 2 lines. Okay, so we're using this geometry. We find, we show that any surface with a maximal number of lines has sort of a special incidence structure. And then we use results from the 70s from finite geometry to say we have this special incidence structure, we can check that has certain properties, we can check that it's a certain size, and so actually we know it's a Hermitian generalized quadrangle. So we know it has kind of the same structure as the Fermat of degree p to the n plus 1, the lines on it. We don't actually know which Fermat, so there's some extra work to be done. And then we sort of reduce algebraically. So maybe I'll say these results. Okay, geometry. This is from, I think, 70. And then eventually what we get is we do some kind of delicate algebra. And what we get is that our surface had to be defined by, and it's actually not going to be the Fermat. What we show is defined by is this. Which we'll see in a minute is pretty directly equivalent to the Fermat. So we reduce algebraic to this thing, which maybe I should have left it up here. One thing you might note is that this is one of those surfaces of the form that we're studying in characteristic 0. It sort of comes with 2 different functions in 2 variables that are the same, and it's kind of a surface of that type. So actually, maybe I want to say slightly more about this proof. What our results in finite geometry say is that they say we have, and this comes from like really understanding this incidence structure, like this set of lines. But they say we have a set of d squared lines, which can be partitioned into B-planes in two distinct ways. So what does this mean actually for our surface? So this tells us that F is of the following form. It's a product of linear forms plus another product of linear forms. And then we can just see these lines directly. So our D-squared lines on F are these V of Li and J. And the 2D, well, the D planes, one way to partition these lines is looking at one way to partition these planes is with the linear forms Li. And then one way to partition these kind of distinctly is with the MIs. But we really had to use our understanding of this configuration of lines from this paper. And it did involve sort of looking at taking a smooth quadrant and intersecting it with our surface and seeing what happens when we get some lines. And then we had to show that we satisfied some conditions that were needed in this finite geometry. So yeah, maybe one thing I'll note is that, yeah, so once we get it sort of to this form, we're able to algebraically reduce to this form knowing some of our geometry. And this is of this form. So right, anything in two variables will split completely into a product of linear forms. So here's one product of linear forms, and here's another product of linear forms. And then you can sort of see at least some of the lines on your surface in this case. You can't see all of them this way, but this gives you D-squared them. All right. Questions, comments? Okay, that's all I want to say about this group. But maybe one thing I want to say, so we say that we achieve this upper bound if and only if we're projectively equivalent to the Fermat. And I kind of already said that there's other things that are projectively equivalent to the Fermat. So maybe one thing I'll ask is what are projectively equivalent to the Fermat? So which surfaces do we have? Question. Okay, it was parents critique. Surfaces are projectively equivalent the Fermat of degree 3 plus 1. And actually, I can ask this more generally. I can put this in any number of variables, right? Like Fermat is like x to the p plus 1 up to w to the p plus 1, but I could add any number of variables and call that a Fermat hypersurface. So I could ask the following question, and maybe, okay, got like 25 minutes. So maybe I want to say, note, so if f is x1 to the p to the plus 1, up to x10 to the p to the plus 1, just adding these. Then we can write, I actually have a beautiful way to write F in terms of a matrix. So I could write a row vector with all my variables raised to the p to the e, times my 4 by, well, n by n identity matrix, times the column vector at x1 to xn. And if you just matrix multiply these out, you'll end up just getting back this form. So if you're bored, you can just verify that really quickly. And maybe I'll write this in a little bit slicker notation. So I'll write this as x. I'm going to think of x as a column vector, so maybe I'll do transpose, and then I'm going to raise it to the p to the e. And that's going to mean just raise every entry to the p to the e. Great, so I'll write it this way. And actually, you can kind of see very explicitly what happens when I apply a linear change of variables. Right, so if I apply okay, so in other words, I'm going to send my vector x to some, this is going to be n by n matrix coefficients in k times my vector x. Okay, so what does this do? This just sends x1 to the first row of my matrix times my variables, and x2 to the second row matrix of my variables, and so on. Then, what does this do to f? Well, I'm just going to apply this to both sets of variables. And again, we're still in k as characteristic p. So freshman stream tells me that if I have a linear term to the p to the e, then I can just pull in all my linear terms. So what does this mean? So it gets sent to, I guess, mx transpose to the p to the e times the identity times mx. But yeah, if you work out what freshman stream means here, well, first of all, I can just do the transpose. I get m transpose, x transpose. And this p to the e can pull into both pieces. So it's going to just raise the p to the e on all the coefficients and all the variables. And that's just because I'm in characteristic p. Maybe I just want to write this. Again, here I just need raise every p to the e. Times our identity times x. Maybe I just take this is going to be in space. All right. So that's what happens to our matrix when we apply linear change of coordinates. We get something else of this form where I have something times the matrix. So my variables to the p to the e transpose times my matrix times my variables. I still have that, but now I have a new matrix in the middle, which is this guy. And so you can ask, is like, which matrices can I actually send to if I start with my identity matrix? And the answer is maybe surprising, but the answer is any full range matrix. I can put here. This is a theorem. This is actually known to many people. So the ones where I can explicitly find it are Beauville 90, who's one as before, and also Shimada 2001, and then also this large list of co-authors in 2022. And we have a really nice version of it that's very simple and doesn't use the same technique, so it's a different group. Maybe I want to write this. I'm going to write this as an man. I will rank. Then there's this, and then there's the variables. Sending after the command. And of course, I should say this is in variables. K is characteristic p. And actually, here I get algebraic closure to make all my linear changes of coordinates. Otherwise, you might not get everything in your field to be able to go with them on. So the things that are projected as ones to the Fermat are exactly the things that can be written in this form where I put a full rank matrix there. Right. Maybe more generally, you could ask, what if I don't have a full rank matrix here? What polynomials do I get then? So, more generally, a feature classifies all projective equivalence classes as polynomials of the form. And maybe I'll say explicitly there are finitely many, and we describe them. And we describe them explicitly. So we get sort of canonical matrices that you can send anything of this form to at least one of those, exactly one of those matrices. The number of matrices we get, at least if you assume that F can be written as smaller number of variables, is the number of partitions of N, or N is your number of variables. Yeah, questions?
That theorem just says that every full rank matrix can be written as M power. It's just a linear algebra result, right?
Yeah, it is.
Can be written as M power.
So, yeah, this is what falls out, is that this is true. Any four rank matrix can be written this way. You have to be a little bit careful. I guess we're in characteristic P here. So, this fact is really using the character, like the fact that we can sort of pull in, powers of like these linear changes of coordinates. The fact that they work like this is using freshman stream. So this is in characteristic P.
My point was it has nothing to do with the F or the Fermat polynomial, right? Like the result is as such.
Yeah, it's a linear algebra result. So yeah, this might be known. I mean, there's we can include some other references in our paper that maybe state this less explicitly, but this is sort of known in other contexts and in other languages. Yeah.
But we cannot go to other polynomials. If I have any random polynomial, you cannot find a change of polynomial or change of variable so that they're same, right?
No, the target is special.
So it depends on if I give a random polynomial.
Yes.
Yeah,
It's very special.
Yeah.
it's a very special polynomial in this form, and I'll talk a little bit more about what these look like. So
If E is 0, these are quadrics. You can
Yeah.
do it as a generalization of quadrics.
yeah, and that's the next thing I'm gonna say. So so maybe let's say that first. Okay, so I want to say one more thing first.
Yeah. Not the same quadrics are most ones.
Actually, maybe I should say their name first. So polynomials of this form, this special form, we call them in our paper Frobenius forms. And that's exactly because they generalize quadric forms, which I'll talk about a little bit more. But they also are known by other names, which we learned later. So they're known by cubics. And Q is a P to the E, so because playing off the word cubic, there's many ways in which they kind of behave like cubic surfaces. So in our paper with Anna, we talk about one way. Raymond has a different way of doing them like cubic surfaces, so their geometry kind of acts like cubic surfaces. And then Shimada calls them quadrics. Again, talking about quadric forms. Unfortunately, we didn't know about all the other language when we.
I think Chen is after ours though. I mean,
Oh yeah, sorry, this one is after ours. Cubics, I think, is
He didn't
after
know about
ours.
ours.
Although I think it was maybe unpublished and written out before ours, but I think anything published with this name was after ours. This one's before ours. Yeah, this is like 23 or so. Yeah, sure.
Yeah, I think I have a bit of a thought question, but Karen was just saying that this is a generalization of the diagonalization of quadratic forms.
Yes.
But what about characteristic two?
So in characteristic 2, you can't write. So there's still something you can say, but you can't write a symmetric matrix. You can still write a quadratic form in characteristic 2 with a matrix, but you can't assume that it's symmetric anymore. So yeah, so there's something more careful to do in characteristic 2.
Okay.
So maybe I'll make one more note and then I'll talk about the projects. So note, if F is of this form, then V of F, I guess I'm viewing it as a projective variety. So I said n variables, so n minus 1. Has a singular locus of dimension. Oh, I should. Okay, well, anyway, of dimension n minus 1 minus rank there. No, I'm in variables. Sorry, n minus 1 rank there. Oh no, this is great. Sorry, n minus 1. Okay, so the only case I get something smooth, so the only case I get something -1 here is when my A is full rank. Otherwise, I get some singular locus. So most of these are singular as projective varieties, except for the Fermat.
Sign error. Oh, no, there's not, never mind.
I don't think so.
No, there's
Yeah.
not.
Great. Maybe another note is that these generalized quadratic forms okay, so any homogeneous degree 2 polynomial can be written and this is where I need Q not equal to 2. Uniquely as this. I can just put in some matrix. This is a n by n matrix with coefficients in K. And I'm assuming that this is symmetric. That's how I get uniqueness. So for Frobenius forms, I don't need to assume that it's symmetric. In fact, I can't because of this P to B on the one side. It will be unique already. It will be a unique representation of that particular polynomial once I pick an A. But and these have sort of the same thing. So they have a singular locus of dimension n minus 1 minus the rank. And when these two, you can say things. We actually have a paper that kind of classifies what happens in characteristic 2, but you have to be a little careful because you don't want to assume it's symmetric, otherwise you get a bunch of zeros. Okay, so in the last 10 minutes, I want to tell you a little bit about, so I think these are really beautiful polynomials, but we weren't studying them just because they generalize quadratic forms. So I think they're beautiful just algebraically, but I want to tell you why we were studying these. And maybe as a reminder, and I'll say a few words for the graduate students in the audience who may not know this, but if F variables, okay, is characteristic P, is homogeneous, then our F threshold at the homogeneous maximal ideal of F is an invariant between between 0 and 1, and measures the singularity of the affine cone over the above. I'm thinking of projective variety at this home point. And I should say maybe this is introduced to Kaji and Watanabe. Also studied by Hara and Rashida, and there's plenty of other people in this room who have studied this and have many results about the F threshold. It's one of Karen's favorite topics, so I didn't leave time to give at least she's better talks before. So I didn't leave time to do a proper introduction to F threshold of a hypersurface. But maybe I'll point you to a beautiful paper by Karen and Angelica Benito and Eleanor Father. So there's a survey. Specifically thinking of this in the hypersurface case, that says a lot and compares it also to the log canonical threshold, which is it's sort of the characteristic P analog of that characteristic 0 invariant. So if you're a graduate student, I recommend this introduction to F threshold. And there's some other things about singularities on that paper. This is from 2013, I think. Oh, and I found out this was in honor of David Eisenbach's 65th birthday. So it's another birthday paper. But maybe the only thing I want to say about this is that, so it measures the singularity at the cone point of the affine cone over this projective variety. And if we're equal to 1, then we're less singular. In particular, if we're smooth, well, okay, we can't be smooth if we're homogeneous here because we're measuring that affine cone point. But if we do this sort of generally, right, we should always get 1. And then in particular, if our meta is F pure, then we should get 1 here, and otherwise we can get smaller numbers here. So yeah, so smaller is worse singularity in this case. So the reason we are studying these polynomials is because of the following theorem. Here's characteristic B. So we've proved uniform lower bounds on all F3 thresholds of any hypersurface of degree D in terms of its degree. So F3 threshold is always actually bigger than or equal to 1 over D minus 1.
So F is reduced.
Yes. I don't want to consider it reduced. Yeah, if I don't assume reduced, then I can get 1 over D pretty easily. This x to the D has F3 threshold 1 over D. Yeah, so I want to take a reduced homogeneous polynomial of degree D, and the F threshold is bigger than or equal to 1 over D minus 1, with equality, if and only if D is equal to P to the E plus 1 for some E, and F is contained in our homogeneous maximally of P to the E. And actually this works greater than or equal to 0. If I plug in E equals 0, I get a quadratic form, and then my F threshold is 1 anyway, so this lower bound holds, but isn't that interesting? And maybe I'll note, so what does it say about our polynomial F? Well, F being my homogeneous maximum ideal, maybe I should say this is 1 over E, yeah, 1 over E, says that F is going to be some things times those guys, right? Space. But then my degree being p to the e plus 1 tells me that the only space I have left is for a linear form. Okay, so this is L1. And these are linear forms. Okay. In other words, I could actually write F as my favorite way to write it. I can take a matrix A, where the first row just gives me the coefficients of L1. And so when I multiply by my vector X, I just get L1, and then L2, and L3, and so on. And then I'll multiply by each of these X to the P to the E. So this is gives us the coefficients of the lines. In other words, we achieve this lower bound if and only if F is one of these Frobenius forms that we've already talked about before. So maybe I'll say, we have 2 minutes. So in this case, when we achieve this equality, we call a hypersurface extremal. Because we achieve the extreme lower bound threshold. So maybe I'll just say a final note. So our theorem can be restated. This is the smooth surface a smooth surface has less than or equal to p to the fourth minus 3d squared, 3d cubed plus 3d squared lines with equality. If and only if X is extremal in the sense of the F threshold. So in the sense of our theorem there. So in other words, these smooth surfaces in P3 with as many lines as possible, if you take their affine cones over them and measure the singularity of that cone point, we get the lowest possible F threshold that we can possibly want. And they're the only smooth surfaces that achieve that lower bound. All right, I should stop there.
Questions? Do these extremal surfaces have a large automorphism group?
Yeah, that's a great question. So this is recorded, right? Well, maybe I can say I think we are epsilon away from proving that they have the largest automorphism group possible. I'm not quite sure it's true in all cases, but we have many cases where if you have a surface with at least one line, I think we believe that they have the largest automorphism group of any surface with at least one line. Yeah.
So these are often also the hypersurfaces, all of whose hyperplane sections are isomorphic, right? Five-OVL.
Yes.
Is there, or all the non-singular hyperplane sections, is there a way to see why like having an active number of lines should imply all your hyperplane sections are isomorphic? Like directly?
Not directly. I don't know. I mean,
both goes back to Frobenius form.
Yeah, I mean, these hyperplane sections are very special, and we get like we get sort of star points, which is maybe what. Yeah, but I don't think there's a way to see it directly. So I haven't thought about it that much, but I don't see a way to do it directly.
Yeah, and they're not all isomorphic, right? I mean, because some of them could be tangent, and then you get a singularity.
Yeah, all the
Yeah,
all the smooth
smooth ones are.
Yeah, all the
You
smooth
get a
ones are.
distinguished set of points on all the sections from the lines, which is a very large set, which is very strong properties.
Yeah, I guess they
Maybe that
come in
confirms it.
by our classification theorem. They come in finitely many types, and we can tell you exactly what those types are, and we can talk about them. But yeah, the smooth ones are all isomorphic. And actually, each one of our types we can kind of. Yeah.
So do you know anything about the lines contained in non-smooth Frobenius forms?
Yeah, we thought a little bit about this. So the non-smooth Frobenius forms, the ones that are surfaces, there are cases with very small number of lines, but we think potentially, oh, and there's one with infinite many lines. There's one with there's one with infinite many lines, and then there's the other ones have finite many lines, and some are small, like I think like 2 or 3. Do you remember how many lines are on the other ones?
There's one with 1, one with 2D, and one with D squared or something.
Yeah, but we haven't thought about it very carefully. I don't
What was
know
the
if we,
question?
so the non-smooth Frobenius forms, how many lines do those surfaces contain?
Oh.
So we have this written up, maybe we haven't.
I think we worked out some cases.
We worked out some
Right.
cases, but what we didn't do is think carefully about the multiplicities. So maybe they have a lot of lines and you consider them correctly, but I don't, at least a priori, there's a small number of actual lines on some of them and then infinitely many on one of them.
Okay, another
yeah.
question. In the smooth case, do you know anything about, like, if I have one smooth Frobenius form and I want to find a projective automorphism to take it to the Fermat one, can I like take a point of intersection of the lines and then send this point to this one and this line to this line, and how many conditions do I guarantee that then the surface is sent to the Fermat one? Yes.
Yeah.
We know exactly.
Yeah, but
You take a grid of 3 by 3 lines, and any grid can be sent to the standard grid.
yeah, so we prove a lot of, actually in this paper, we prove a lot of things about the automorphism group of that surface, and so we prove it's like transitive on sets of 3 lines, and actually it's transitive on sets of 3 by 3 grids. So lines often come in these configurations where there's 3 skew lines and then 3 other skew lines. So we have a lot of results like that. As far as like coming up with the explicit matrix to transform it, we can tell you sort of how to play with these, like what each matrix does, but I don't think we have an explicit in this paper. But I don't think we have an explicit, like, I don't have a Macaulay 2 thing that you plug it in and it tells you which matrix to do, but you could, there's definitely things in here that you could use to kind of figure out which change of variables to
Yeah,
use.
if you can identify them to start point, if you can write down the start point, you know, the intersection.
Yeah, that you can send it to.
Yeah, and
the
you can
start
send it
point
to
on
start
the
point
Fermat.
or not.
Yeah, and we have written down like what the star points are on the Fermat. So yeah, I guess that's true. If you find a star point and then you can send it to our star point and maybe you just need to find 4 points and then you fix it. Yeah. Great.
Do you know anything about the distribution of this upper bound in the case that you don't have an algebraically closed field? Like you gave an example of when you achieve this upper bound.
Yes.
But do you know how like
Okay, so if K is F P to the 2E, then the Fermat has all of these lines. So if I go smaller, then I lose some of the lines. So I guess the reason I am assuming algebraic closure is because if I have a smaller field, and I take, like there are other surfaces not projectively equivalent to the Fermat over this field that also have that number of lines, but they're projectively equivalent over the algebraic closure. So this like nice statement about equality if and only if, well, actually this is true, I guess. There is still equality if and only if they're extremal. But to say they're equality if and only if they're the Fermat, we need the algebraic closure to do the change of variables. But yeah, this is the smallest field where you see all the lines. So if you look at F P to the E, and you don't see all the lines. But we see them all here at
I
least.
mean, if you could pass to the algebraic closure, then you'd see all the lines, and then thered be like a Galois action that would group some of them together, that would be defined over your original field. Does that make sense?
yeah.
Yeah.
I think I have another question. So in this bound, do you have the next bound? Like if this is not rich, what is the next thing?
Yeah,
or it can be like
That's
just
a
only
good
one?
question.
That's a great question. We've thought about it a tiny bit, but not very hard. And the very first naive things we can try very hard, but the very first naive things we did, we were trying to just construct something with a number of lines between this number and the characteristic 0 bound, and we didn't find one right away, but we haven't exhausted this. So I think this would be really interesting. I would love it if there was some beautiful theory that said, if you have slightly less lines and you have a slightly bigger F your threshold, and there's some nice connection between lines and F your threshold, but I don't know it yet, but that would be a dream, yeah.
Okay, well, if there are other questions, we can thank Jyoti.
Hold on, one.
Okay.
One last thing.